Hello students, in this video we will discuss various methods of formation of aryl halides which are also called haloarenes. So first question comes to mind is that what are haloarenes? The answer is quite simple, that any molecule in which there is a direct carbon halogen bond where carbon must be in a aromatic ring. For example, in case of chlorobenzene, we have a carbon halogen bond in which carbon is part of aromatic ring, whereas in case of benzyl chloride we have a carbon halogen bond, but this carbon is not a part of aromatic ring. So by this definition, this is benzyl chloride, this is not aromatic, whereas chlorobenzene is definitely, we know, a aromatic compound. So clearly, to a molecule to be called aryl halide or haloarene, halogen must be attached directly to the aromatic ring. Moving on to the various methods of synthesis, the first method is direct halogenation or nuclear halogenation. In this method, direct halogen is reacted with the aromatic compound. These halogens are chlorine, bromine and iodine, and a halogen carrier such as AlCl3 aluminium chloride, ferric bromide and sometimes FeCl3 is used. So coming on to the reaction, the general reaction is case of benzene which is treated with halogen by using a catalyst which is halogen carrier heated at a temperature of 310 to 320 Kelvin, and we are getting a haloarene as a final product. So taking example, benzene can be reacted with chlorine, FeCl3 will be the catalyst, 310 to 320 Kelvin, and what we get is chlorobenzene. Similarly, if you carry this reaction with FeBr3 and bromine combination, then bromobenzene will be the final product. And you have to remember that you can only use chlorine and bromine in this reaction to get effective yield. So moving on further onto the mechanism of this reaction. What is the mechanism by which halogen is being added to the aromatic ring? Since aromatic compounds are electron rich, therefore we must have an electrophile to react with them. So this is what happens when chlorine gas reacts with FeCl3 ferric chloride, it generates FeCl4 minus and chlorine positive ion. This is our electrophile. This will react with the aromatic ring. So this is the second step of the mechanism, reaction of electrophile with the aromatic ring. So what happens? Let's have a look. What happens? That one of the bonds of the aromatic ring, they are attracted towards the electrophile. So this results in formation of a carbocation. At one side chlorine is added, whereas at the other end positive charge is generated. Now this carbocation can undergo resonance. That means it can have more than one structure like this. Therefore, we can say this carbocation is stable because reaction will only go further if the intermediate formed is stable. It is also called Aryl ion. Why it is called Aryl ion? Because positive charge is present on aromatic ring. That is why this is called Aryl ion. So in the final step, Aryl ion loses a proton to give final product. So let's have a look what happens. Choose any of the above structure of Aryl ion. So this is positive, this is chlorine, this is hydrogen. Now this Aryl ion loses this proton to give you the final product, which is chlorobenzene, and the H positive ion thus produced, it reacts with FeCl4 minus to give you HCl and FeCl3, which is the catalyst. So it is formed again to catalyze the further reaction. Why this reaction, this step is faster? Because this is not aromatic, but this is aromatic. Therefore, we are going from a non-aromatic molecule to an aromatic molecule which is more stable. Therefore, this last step of the mechanism is the fastest step in the reaction. Now, what are the important points which we should remember for this reaction? First is, if an excess amount of halogen is used, then we will get mixture of products. For example, if we use chlorine which is in excess in the same reaction, then we will end up with a mixture of 1,2-dichlorobenzene and 1,4-dichlorobenzene. So this is what we do not want in an organic reaction, that mixture of products are formed. Similarly, if substituted aromatic compounds are used, such as toluene, then we again get mixture of products, that is ortho isomer as well as para isomer of chlorotoluene. This is the shortcoming of this reaction, that whenever we use excessive of halogen, then we will get the mixture of products. Then again, if we start with substituted compounds, then we will get mixture of products. Moving further, there is a question which is generally asked: why haloarenes are difficult to prepare by direct halogenation? The answer is that reaction with the iodine is reversible because the hydrogen iodide formed is a strong reducing agent. So it forms iodobenzene and reacts with it to give back the starting material. To overcome this, the reaction is carried out in the presence of oxidizing agents such as HiO3, nitric acid, and mercurous oxide, which destroy the hydrogen iodide formed, which results in shifting of equilibrium towards the forward reaction. Now moving forward, second method to obtain haloarenes is using diazonium salts. It is also known as Sandmeyer's reaction. What happens is this: when aniline is reacted with a sample of NaNO2 and HCl along with temperature of 273 to 278 Kelvin, then it is converted into benzene N2 positive Cl2. This is what we call benzene diazonium chloride. What is so special about diazonium salt is that N2 positive is a very good leaving group. Even it may be called as a best leaving group. Therefore, it can be easily replaced by any atom with negative charge. That means we can react this with a nucleophile. For example, again, the reaction of benzene diazonium chloride with cupric chloride Cu2Cl2 in presence of HCl results in the formation of chlorobenzene. Similarly, if the reaction is carried out with cupric bromide in the presence of HBr, then bromobenzene is obtained. And on the other hand, if the reaction is carried out with potassium iodide, then we get iodobenzene as the final product. Therefore, cupric chloride and HCl mixture gives you Cl minus, potassium iodide gives you I minus, and the mixture of cupric bromide with HBr is equivalent to bromide ions. These ions basically replace the halogen from that diazonium salt. So, it is the best reaction to replace or to add halogen to an aromatic ring. Now, fluorobenzenes are prepared from diazonium salts. We will start with benzene diazonium chloride and react it with fluoroboric acid, that is HBF4. This HBF4 will give you F minus ions, which replaces the nitrogen molecule to give fluorobenzene as the final product. Fluorobenzene, and this reaction is believed to undergo through an intermediate in which the chloride ion is first replaced by BF4 ions. this intermediate is further converted into the final product. This reaction is known as Boltzmann reaction. So it is also a naming reaction. The next method is known as Gattermann reaction. What is so special about it is that it is modification of Sandmeyer's reaction. And how it modifies it? It uses copper powder instead of cupric halides. So this is the modification. Other whole process remains same, that is benzene diazonium chloride is treated with copper. This is in the powder form in presence of HCl, will give you the desired chlorobenzene product. However, in the Sandmeyer's reaction, we were using the cuprous halides, that is Cu2Cl2 in presence of HCl to reach at the same product. So this is Gattermann reaction and this is Sandmeyer's reaction. So only difference among these two is the copper species which both reactions are using. The next method is Hunsdiecker reaction. In this reaction, an aromatic salt is converted into its silver salt, that is COOAg, that is silver salt, which is further treated with bromine in CCl4 as a solvent, and the mixture was refluxed to obtain bromobenzene as the final product. So this method is only specific for bromoarenes. This reaction undergoes a radical mechanism because free radicals are produced in this reaction.